Okay, so today we are going to discuss our last topic, and these are plasma oscillations. We will be looking into the conductor, okay, and we will be looking into this exceptional case where epsilon effective can be potentially zero. Okay, but to get there, let's consider one of these four Maxwell equations given over here. As we discussed before, if we substitute at the plane wave solution, okay, use the Ohm's law, continuity equation, we'll get the dependence of rho on x and t substituted over here. The same for electric field, we'll get this algebraic equation, okay, equals zero. Okay, and so far we considered the case when this scalar product is zero, right? So the scalar product is zero, and therefore we didn't care about the prefactor. But now, what if this prefactor is zero? If this prefactor is zero, then the scalar product of k dot e doesn't have to be zero. Okay, well, generically it will not be zero then. Okay, so to discuss this situation, we will consider low and high frequencies, not just to simplify this discussion. Let's start with the low frequency. Okay, so let's consider low frequency. So the low frequency is this epsilon effective, and this bracket is just epsilon effective. This epsilon effective is given by, well, the real part, all right? So the real part, epsilon 1, I'm just not even specifying what the real part of epsilon is, but it's just some epsilon 1. So it's epsilon 0 plus, corrections, plus, okay, so here we will have also contribution from the imaginary part. It will be the imaginary part of the epsilon, it's epsilon 2, right? It's the imaginary part of this, plus this contribution over here, where I use the fact that at small frequencies, sigma omega can be just approximated by sigma dc. So all in all, this is approximately given. So if I look at small frequencies, that this term dominates over the first one here, over this guy, and therefore all in all I will get this result here. So now this can be zero in principle, so I can set this to zero. If I set this to zero, then the frequency will be purely imaginary. The frequency is going to be purely imaginary. It's kind of weird. But let's just substitute this into our wave equation, into our wave form, and then we will get the following solution. Okay, inside the conductor, where we see exponential decay of the frequency in as a function of time. Okay, well, that it means that if you put a low frequency wave into the conductor, it will decay, okay? It will decay not even in space, so in space, it decays in time. Yeah, so previously we seen the skin effect where the decay was in x, so now it is a decay in time. So not interesting solution, okay? Not interesting solution. So and therefore this low frequency regime is probably not the best to study interesting behavior of our waves when our effective dielectric constant is zero. So now let's consider high frequency limit. Well, and last time we derived it in the high frequency limit. I can write E epsilon effective as epsilon 0 times this factor where we have 1 minus the omega plasma squared divided by omega. Okay, so when is this 0? Well, it's kind of simple equation to solve. This is 0 when the frequency of the wave equals exactly to the plasma frequency. Okay, and in this case, we will get a propagating solution. Okay, right, so we just take this frequency, we'll substitute into our into our equation. This is, we will get the perfect propagating solution shown over here. Okay, and what's interesting is that in this case E will be parallel to K. E will be parallel to K. As a matter of fact, so then you can also just consider what will happen to the magnetic field and just look at the Maxwell macroscopic Maxwell equations, and you will see that the magnetic field in this case will be exactly 0. Okay, it's just because B is given by your proportional to K cross E, okay, and since K is parallel to E, then this will be just 0. Okay, so for this longitudinal, and this is called longitudinal wave, and for this longitudinal wave, if you just well, take this, take the Ohm's law, take the continuity equation, as we done last time as well, right? So you take all of this and you substitute it over here. As a matter of fact, you can see it also from this expression here, right? So this is K dot E, right, equals rho. Okay, so what it shows here that rho will be given, again, from this equation you can read off, is rho is given by K dotted with E times this exponential. Okay, just substitute E into there. Okay, and normally this factor is 0 in this way, just the rho is 0 too. But in this case, right, in this case, when you substitute this longitudinal wave into the solution over here, into rho, you're not getting 0. You see, because K is parallel to E now, you see that the density oscillates as well. The density of the electrons in the conductor will also oscillate, and these are called plasma oscillations, and they happen exactly when the frequency equals to the plasma frequency, and that's the name. Okay, that's the name, is due to the plasma oscillation. By the way, so that effect always happens when the frequency equals to the plasma frequency, but in this case, K, the wave number or wavelength in this case, right, can be arbitrary. Okay, it happens at a given frequency, but an arbitrary wavelength or wave number. That's it. It was my pleasure to work with you. So, and I wish you the best of luck on your exam. For the Friday, I will do a review of the last midterm number 2, and then I will switch back to reviewing. Well, I will also review midterm 1, and then I will start reviewing the topics as we covered them for the preparation for the final exam. And I will also lay out what will be the form of the final exam on Friday's video.